Okay, folks, we are beginning the final leg of our journey in Algebra 2, where we're going to finish up this lesson 10.3 on ellipses and then get ready to test over what we've learned about circles and ellipses and then eventually just start reviewing for our final exam. So in Lesson 10.3, we've done a lot with ellipses, but there's just a little bit more we need to do. We've learned about some properties of ellipses, and we've learned to write equations that describe them, and we put those on our graphic organizer last week. We're going to relate it to elliptical orbits or to elliptical objects in the real world. We want to be able to determine the area of an ellipse, which we've practiced previously, and we'll practice some more here. And then we want to be able to graph transformed images of ellipses, and that's where our focus is going to be here primarily in this part of the lesson. So here's an example where I give you some information about an ellipse, and I ask you to identify the vertices, the length of the major axis, minor axis, and the area of the ellipse. Well, the first thing I want you to notice is that the foci coordinates are given, or a focus coordinate, both of them are given, excuse me. And I know when I look at my graphic organizer that from the foci I can determine the value of C. So I can tell that C is 10. And we want to remember that A, B, and C are always positive numbers. Now I also want to notice that the coordinates of the foci are given such that I can see that they are on the y-axis, which makes this a tall ellipse because the foci always sit on the longer axis. And so the focal constant then, if we look at our graphic organizer, is going to be at 2b. So we're told the focal constant is 38. That means that 2b must be 38. And so when we divide both sides by 2, we find that b in this case is 19. Now the only thing that's missing is our a. We know with b and c we need our a. So again, when we look at our little organizer, we know that c squared on ellipses can always be found by taking bigger squared minus smaller squared. And in our case, bigger is going to be the b's because they're on the vertical or major axis in this case. So let's plug in everything we know. We'll have 10 squared is equal to 19 squared minus a squared. So 100 is equal to 361 minus a squared. And now we want to solve for a squared. So we see that 361 is added to it because this is really plus the opposite of a squared. So I'll subtract 361 from both sides of my equal sign to get negative a squared. And to get rid of that negative, I just multiply both sides by negative 1. So a squared must be equal to 261. When I square root to find a, the square root of 261 is about equal to 16.2. Okay, so the vertices on a tall ellipse we see from our cheat sheet are 0b and 0, negative b. So I know b is 19. So I have vertices at 0, 19 and at 0, negative 19. The major axis is on a tall ellipse, we see again on our cheat sheet, is 2b. So the major axis will be 2 times 19 or 38. It's the same as the focal constant. The minor axis we see on our cheat sheet is 2a. So that would be 2 times 16.2, which would be about 32.4. And finally, the area of our ellipse is found by taking pi times a times b. That's true of all ellipses. And so in our case, that would be pi times about 16.2 times b, which is 19. And that comes out to about equal to 307.8 pi. All right, there's a lot of good stuff in that example. So that's another example of finding the equation in pieces and parts of a ellipse that is a tall ellipse. Well, we also want to be able to graph these ellipses given some information about them. So in this example we have in our notes, we're asked to find the equation of an ellipse in standard form with foci 0, 10. Oh, sorry, same example, excuse me. We want to be able to graph that ellipse. So going back to our previous slide, we found that our vertices and co-vertices can be determined by 0b, 0, negative b, a0, and negative a0. And those, I'm looking now and I see that the grid I've provided is not nearly large enough, so I'm going to pause and renumber my scale. Okay, I changed my mind because it's getting pretty messy, so I'm going to wait and show you how we take that information and graph it with an example there. Okay, here's example 6 that I believe I have in your notes, where we're asked to consider this equation with the ellipse 6x squared plus 4y squared equals 24. Well, what you're going to notice in this case is that it doesn't equal 1 like they always do. Well, it's simple to get it equal to 1. All we need to do is divide everything by 24, and then it will be equal to 1. So when I simplify this, if I type 6 divided by 24 into my calculator and then do math frac, I find that that's 1 over 4. So this is 1x squared over 4. If I type 4 divided by 24 in my calculator and do math frac, that reduces to 1/6. So this is y squared over 6, and that equals 1. Now it's in a form that we recognize. Notice b squared is bigger than a squared. So this must be a tall ellipse. So we know to go to the tall ellipse portion of our graphic organizer to determine some values or some pieces and parts of this ellipse. So first, the vertices of a tall ellipse are at 0b. Well, since b squared is 6, then b must be the square root of that. So we have a vertex, at 0 square root 6, but also at 0 negative square root 6. The length of the major axis, again, on our tall ellipse we see on our graphic organizer is 2b, so that would be 2 times the square root of 6. The length of the minor axis, we know, according to our graphic organizer, is 2a. Well, a squared is 4, so a must be 2. So it's going to be 2 times 2, which is 4. The foci, I need to find c. And so c squared is equal to bigger squared minus smaller squared. And if I substitute b squared minus a squared into that equation, I find c squared is equal to 6 minus 4, which is 2. Well, that means then that c must be equal to the square root of 2. Now the foci are on the major axis. So if you're looking at your graphic organizer, the major axis is the vertical axis on a tall ellipse, and so we see that it will be 0c, so 0 square root 2, and 0 negative c, so 0 negative square root 2. Finally, the area of this ellipse is pi AB, as it is for all ellipses. A we know is the square root of 4. B we know is the square root of 6. So when we multiply pi times 2 times square root of 6, we get 2 pi square root 6. There's the area of our ellipse.
Keen's out planting flower pots.
Mm-hmm.
You should go over and find out what we own for those tickets.
I'm in my pajamas, I will later.